Good morning.
Yeah. Okay, girls. Good morning. And before we start, does anybody have any questions yet? No? Hey, ladies. So today we're going to be talking about aliasing. And first of all, it's okay because it's okay. An aliasing, that's going to be an artifact of Doppler. Okay. We later on in general we'll be talking about different kinds of artifacts in chapter 21. We may later on in this chapter here talk about, we can say, some other artifacts of Doppler as well. Okay. And mainly in chapter 20, how to, mainly we can say, get rid of these other diverse artifacts here. Or mainly or me is how you can say is try to fine tune your image. Now, first of all, yes, what is an artifact? Now, usually it's when I ask students, they say it's something that is very, very old. No, that's not what an artifact means. Okay. You can say as if you dug up something which was very, very, very old. Right now, it's just saw on the news that they found a shoe which is 2,100 years old. Let's say it's this is what they got out, and let's say it's this could be the shoes, or what may be a shoes, or a shoe. What they mainly need to do is first remove, a lot of things that has accumulated on top of it. And that is going to be the artifact. But you end up with this me is okay, going to be okay, this 21-year-old or 21-year-old shoes. Clear? Okay, so artifact is mainly going to be against okay, the dust on the lamp or the rust or soil or whatsoever. That mainly is okay, makes it, as you can say, is okay, impossible for you to guess what it is that you are looking at in the first place. Yeah. So bias, okay, removing of the artifact, then we know, okay, this is whatsoever. So likewise, okay, when we see artifacts on an image, on a recording, okay, that is actually as okay, going to as okay, make it difficult for us to actually as okay, determine what we are looking at. Because the image that we had is actually as okay, going to be affected by artifacts. So it's going to be as okay, a removal of the artifact that actually will enable us to just okay, say, okay, now this is actually just okay, what we are looking at. Did that make sense? So one of the common artifacts of your Doppler is going to be as okay, what we're calling aliasing. This is just one type of artifact that is mainly as okay, going to be seen in Doppler exams. Did you ladies get that? Did you ladies get that?
Yes.
Okay. Now the next question, okay, is why is it called aliasing? Well, okay, just look at the word alias. Does anybody know what an alias is? An alias? Yes, ladies.
A false
Right.
identity?
Huh?
Like a false identity?
No. Anybody can read that off from the book. I guess none of you have ever filled out forms. Now, you may fill out a form and okay, yes, right next to it, okay, where you fill your name is going to be written alias. What does that mean?
Like if you have another name that you go by?
Exactly. Which is not really your real name, right?
Right.
Okay. So that's an alias. Because okay, if they are looking for okay, you can say okay, verify your identity, who you actually are exactly. If I come and say, well, okay, I'm looking for Tiffany. That's okay. The people who Tiffany said, well, okay, they know me, but they know you under another name. They just call you Tiff,
Yes.
right? Okay. Okay. Or you can say it's okay, King, or whatever. Okay. So if I say, well, okay, do you guys know a person called Tiffany? And they'll say, no, we don't know Tiffany. We know a Tiff, but we don't know whether her name is Tiffany. Right? Okay. Clear? Okay. So this is going to just, okay, that's an aliasing. And ladies, the main reason that, okay, yes, this artifact here is going to be called aliasing is because positive Doppler recording is going to be shown as a negative Doppler. Yes, okay, if you go vice versa and say, well, okay, a negative recording or a negative Doppler shift is going to be shown as a positive Doppler shift. So this is going to be as okay fake. This is going to be fake. Now we all know that, okay, as Tiffany's name is Tiffany, but she may go under as okay a fake identity, an underscore name, which is Tiff. Clear? Okay. So what actually is okay was a positive Doppler shift. Part of it is going to be as okay shown as negative. And what actually was a negative Doppler shift, part of it is going to be shown as positive. Is that clear?
So it's just gonna be switched around?
No. Okay, it's not going to be switched around because, okay, there is an if to this. Okay. Now, one thing that I said the other day when we talked about is, okay, different kind of Doppler modes. We said, okay, as aliasing, all right, let me check this. We say it's okay, pulsed wave Doppler. That was mainly as okay, where we will see aliasing. So aliasing is primarily going to be something that we will see in pulsed wave Doppler. Is that clear?
Okay, yeah.
Okay. Now, if you remember, yes, okay, what I talked about pulsed wave Doppler, that's okay, the main negative point or disadvantage of a pulsed wave Doppler was that it had I was only going to be able to just, okay, measure lower velocities or low velocities, which was anything between 3 to 5 meters per second. Okay, where we say that, okay, yes, if you, for instance, okay, are able to just, okay, measure up to, let's say, 5 meters per second. Well, okay, that's going to be, we can say, okay, our max velocity that we are going to be able to record. Okay, but if blood flows at a velocity that is greater than 5 centimeters per second, then that extra velocity is going to become recorded as either a false negative or a false positive velocity, which will be called aliasing. If that makes sense.
Not to me.
Not to you. That's fine. It's too early to make sense. Well, Shaq, you should You should be happy for this because you're the one who benefited. When the police couldn't measure that you were going, yes, okay, 300 miles an hour. Because they could only record up to 300, that's okay, 150 miles per hour. So you can say, okay, that 150 miles per hour, do you speed it beyond their ability to scan? In Doppler, that's okay, that is going to be shown as aliasing. Okay, so, okay, girls. We can see now, you may, as okay, if you look in your book, come across something which is called the Nyquist limit. Okay, ladies, this Nyquist limit here is actually, it's okay, that's going to be, it's okay, we can say it's okay. And max Doppler frequency. Or we can say it's okay, this could also be referred to as a max Doppler shift. Right, okay. Then we already know that, okay, as your Doppler shift or Doppler frequency is mainly as okay, and is actually as okay a frequency. Okay, which is derived from the difference of the transmitted frequency, reflected frequency from the transmitted frequency. Okay, but to make a long story short, girls, this Nyquist limit here is mainly as okay going to be as okay the max velocity that we are able to record. Did that make sense? Okay, but it says, okay, this velocity here was actually, it's okay, determined based on, it's okay, your Doppler shift or your Doppler frequency. Because your system determines the velocity of blood into, it's okay, all dependent upon, it's okay, the difference of the two frequencies, the transmitted and the reflected frequency. But we translate that Doppler shift frequency into velocity of blood. Clear? Did that make sense? So the maximum velocity, the highest velocity that you were able to record, that is going to be considered as your Nyquist limit. Now, goes that's why it's okay. The other day when we did spectral Doppler, for instance, we said, okay, this one here was your baseline, and we already know that, okay, that's going to be representing, okay, as a Doppler shift of 0. Did that make sense? Yeah. Where we said, okay, yes, ideally, as okay, anything above the baseline is going to be as okay, positive Doppler shifts. And or as okay, where that was going to be as okay, below the baseline will be, sorry, negative Doppler shifts. Did that make sense? Right, okay. Now we said, okay, as that we had said, okay, as our Doppler shifts, we said, okay, here. like this. Let's just say that, okay, as it goes by 10. So it says, okay, 10 centimeter per second, 20 centimeter per second, 30 centimeter per second, 40 centimeter per second, and we can say, okay, 50 centimeters per second. At this point here, ladies, this 50 centimeter per second on the positive side, that is going to be as okay, your max positive velocity. Or Doppler shift that we will be able to record. Did that make sense? Where, okay, so if you go on to the negative side, we say, okay, right now, 10 centimeters per second, 20 centimeters per second, 30 centimeters per second, 40 centimeters per second, and let's say it's okay, 50 centimeters per second. But okay, we already know that all these here are negative Doppler shifts. So what would that mean? That may mean that, okay, as 50 centimeters per second in a negative velocity, in a negative Doppler shift, that was the maximum velocity that we are going to be able to measure at this point here. Did you girls get that?
Yeah.
So currently, yes, okay, let's say it's okay that this is our setting. So yes, okay, if we record a positive Doppler shift, the max that we'll be able to record would be 50 centimeters per second. Max negative Doppler shift could be as okay, 50 centimeters per second. Where positive or negative mainly as okay is all dependent upon as okay the direction of the blood flow in relation to the transducer. We learned more about that, or we got more specific about that. Yes, okay, the other day, or this Friday. Okay, where we is okay at the end of the class talked about yes, okay, how to determine the direction of the flow. All dependent upon is okay whether we saw a positive Doppler shift or a negative Doppler shift related to yes, okay, to your beam and or okay your sample gate. Okay, but right now we can say it's okay this speed here, 50 centimeters per second on the positive side and or minus 50 centimeters on the negative side. That is going to be as okay be your Nyquist limit. Did you girls get that?
Yes.
Good. Now let us just say that okay, yes. In our instance here is okay, the blood flows at a velocity of let's say okay, yes, the velocity of blood is 70 centimeters per second. Well, let's not go velocity. Let's just say it's okay. Just for instance, say it's okay. Speed. Okay. Now, for instance, okay, if this was positive, if we had a positive Doppler shift where the blood was flowing at a speed of 70 centimeters per second, but our Nyquist limit or the max limit that we were able to record was going to be 50 centimeters per second. And we said, okay, that we had a positive Doppler shift. Now, well, okay, your first 50 centimeters, no problem. But we actually is okay, where we are is we are missing. Well, okay, this is just going to be, it's okay, 20 centimeters per second. Right, okay, which we aren't able to record here because it's okay, the speed that we are able to record was maximum 50, but the blood is flowing at a speed of 70 centimeters. Clear? Now, what is going to happen is this remaining 20 centimeter, ladies, is going to be shown down here. I should have been a little bit short. So this is the aliasing. Okay. Why do we call it an aliasing? Because, okay, what we actually had was a positive Doppler shift. But what we see here is that, okay, as some of that positive Doppler shift, which we're not able to record because of, yes, okay, the Nyquist limit, which was lesser than the speed of blood, is going to show up as, okay, as in this case, as a negative Doppler shift. And that will be as, okay, what we call aliasing. Likewise, girls, if we just go the other way around and say, yes, okay, what if we had a positive or a negative Doppler shift? Right? Whereas, okay, our velocity was, our speed was 70 centimeters per second. But our recording capacity, our setting was set to, yes, okay, only be able to, yes, okay, record negative velocities to 50 centimeters per second. Now, I mean, it still mean that, okay, yes, these 20 centimeters per second here are going to be shown up here. Okay. And mainly because, okay, we actually had, okay, yes, a positive Doppler shift. But our recording, yes, okay, gave us, okay, yes, the false impression that we also had, okay, as a negative Doppler shift. This is going to be, yes, okay, your aliasing. So mainly as, okay, the tip of this actual positive Doppler shift is decapitated and, okay, is shown as a negative. Or this tip here, which was 20, yes, okay, just another, yes, okay, remaining 20 centimeters per second. Because our limit was 50 centimeters, but the speed at which the blood was flowing was, let's say, yes, okay, 20 centimeters. This part, which couldn't be recorded here on the negative side, is going to just, okay, be shown at the positive side. And this will be, yes, okay, your aliasing. Okay, which mainly as, okay, gives us, okay, as the false impression that we have both negative and positive Doppler shift. Likewise here, it gives us, okay, as the false impression that we have both positive and negative Doppler shift. If that makes sense, where we can say as okay here, this is okay an actual reading, but because our Nyquist limit or our speed limit that we are able to record is set as 50, and the speed of blur was greater than 50, that remaining is going to just okay be shown as aliasing on the negative side. Or when we had okay as a negative Doppler shift, where we as okay as said okay our max negative Doppler shift at 50 centimeters per second, but the blood is still flowing at a speed of 70 centimeters per second. Well, okay, yes, this here is a real recording, but it's not going to be able to record these extra 20 centimeters per second of the velocity here, because that is beyond our speed limit or beyond our Nyquist limit. So that is going to just okay be shown as aliasing. Yeah, okay, as this means okay gives us the impression that we also had a positive Doppler shift. This here gave us the impression that we also had a negative Doppler shift along with the positive, or a positive along with the actual negative. Did you ladies get that?
Yes, I can understand now.
Okay. Now, please, 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 please keep in mind. Okay, now when we say yes, okay, spectral Doppler, for instance, like this, you can mainly say, okay, whatever velocity you have up here. Is the maximum positive Doppler shift. And mainly because we consider this as okay as being the maximum that's going to be as okay what we just now recall as okay the Nyquist limit. Yeah. Whereas okay as on the other side, this would be as okay the maximum negative Doppler shift that we are able to record. But please keep in mind that okay, this is just going to be it's okay your Nyquist limit. So an easiest way to yes okay, that's okay, you can say define your Nyquist limit is the maximum speed that you're able to record. Clear? Okay. Where okay, yes. This value here is okay, it could be anything numerically. This value here could be anything. They could be the same, they could be different. And why is it that we will make them different? Yes, okay, we will talk about that in just a little bit. Okay, there, okay, yes, as far, okay, as the positive factor is concerned, whereas, okay, as the negative factor is concerned, as okay, that is only as okay going to be as okay determined by the direction of the blood flow. Clear? Okay. So Nyquist limit is mainly as okay, just going to be as okay that upper limit that you were able to record. Okay, so what I mainly said, okay, yes. if we had a positive Doppler shift, where the velocity is greater than the actual limit. This missing part here is going to be shown here. From the maximum negative Doppler shift and upwards. Whereas, okay, in the other case, if we had a negative Doppler shift, where we can mean it says, okay, we had, okay, yes, where the velocity of blur was greater than the maximum speed. Okay. Where the okay, velocity of blur was greater than the maximum speed that we could record, or what we call the Nyquist limit. This here is going to be shown up by the maximum. So this will be your aliasing. This here is your aliasing. Is that clear? The call goes in chapter 21, or chapter 20, sorry. Where we may see that in your, yes, okay, we said, okay, yes, positive Doppler shift, aliasing or not. What you normally will have is a slight negative Doppler shift like this. Whereas in negative Doppler shift, aliasing or not, you may have a slight positive Doppler shift. Okay, where you mainly say is okay that this here is okay going to be okay close to your zero Doppler shift line. From negative, yes, okay, a slight positive Doppler shift. From positive Doppler shift, yes, okay, you have a slight negative Doppler shift. Okay, where we can mean is okay, just okay, it's okay. Mark these two here, and what they will be referred to as, that will be as okay, what we will call flow reversal. So just remember that, okay, your flow reversal, that is pretty normal. That's what normally will happen. Okay, where you mainly see is okay that in positive Doppler shifts is okay, you have a slight negative low velocity, low negative velocity is okay. Okay, why is going to be as okay a low negative velocity? Because it is closer to the baseline. Because it's okay, this will just have been, let's say it's okay, 2 centimeters per second. Likewise, this will also as okay, just have been okay as a low positive Doppler shift, along with the negative Doppler shift, which is going to just okay be, because that's okay, 2 centimeters per second. So that is more. Where okay, as this here is going to be as okay, anything greater than 50. So this is actually going to be as okay, it's okay, meaning it's okay between 50 to 70. That's speed limit. Okay, which then is going to be shown down here by the maximum negative line. And likewise, if this, for instance, that we had, okay, is a negative of 50 centimeter, but okay, yes, the speed limit here was, okay, let's see, minus 70, then this hump here, or actually as I represented from, it's okay, minus 60, because then minus 52, minus 70, but it will show up here at the positive maximum line. Is that clear?
Yes.
Any questions?
Yes, the nitrous limit, it's adjustable, right? You could change it. You could change the limit.
Yes, we can change it.
Okay.
Okay, now how we change it, we will just come to that in just a little bit. Right, okay, okay. But we can mainly, as okay, say now why and how is it that we get aliasing? A main reason for getting aliasing is, well, first of all, okay, we only see this in pulsed wave Doppler mode. That was something that we talked about as okay when we did our pulse wave Doppler. I talked about that. Right, okay. Now, if you remember, yes, okay, your pulse wave Doppler, we mainly said, okay, yes, okay, that's sample window. But it's not really the sample window that is going to be as okay of importance. It's mainly as okay going to be the depth of that pulse wave window. That would be as okay an important factor. Right, okay. So in pulsed wave Doppler, what we mainly as okay at that point as okay referred to, we said that we had a sampling rate. Which we as okay now just can call here as okay. We can just say as okay that there is going to be as okay your Nyquist limit. So whether you put it this way and say it's okay that the sample rate or your sampling rate or your Nyquist limit, if that is going to be as okay lesser than the velocity of blood, what that actually is okay will lead to is ADAs. Clear? Whereas on the other hand, if you said that okay, as if this sampling rate here, which we also as okay call the Nyquist limit, if that for instance okay is greater than the velocity of blood, that is actually as okay how we may get rid of aliasing. Did you guys get that?
No, can you go over it one more time, please?
It's written that if your sampling rate and Nyquist limit is greater than the velocity of blood, that's how you actually is okay, you know, maybe one of the ways by which you actually is okay get rid of aliasing.
Okay, thank you.
So if the velocity of blood is greater than your LES, okay, Nyquist limit, that will lead to aliasing. Whereas on the other hand, if you see as okay, the Nyquist limit is greater than the velocity of blood, you will not have EDGing. Just look at it in this way, my dear. Let's go here. So. Let's say that, okay, yes. That's going to be so similar as, okay, spectrums. Because the size of the spectrum doesn't change. They remain the same. But let's just say that, okay, as the velocity of blood. Let's say it's okay that we say is 60 centimeters per second. Clear? Let's just say, okay, since we say it's okay, velocity is okay, we have a positive Doppler shift, for instance. But it could be negative. That's our velocity of blood. Now, if you find that, okay, here I have set our Nyquist limit at, okay, let's say it's okay, 40 centimeters per second. On the positive side, and okay, likewise, it's okay, here was minus 40 centimeters per second. On the negative side. And what did we say that this here was? This or this one here is okay, were our Nyquist limit, right?
Right.
So what can you see now? What can you say now that, okay, at the Nyquist limit in this case here is okay, was lesser than the velocity of blood, right? Because I agree, I hope everybody can agree that, okay, yes, 40 centimeters per second is less than 60 centimeters per second. Right?
Right.
So what could we actually say that, okay, yes, well, okay, as we had a positive Doppler shift, that we could measure up to, yes, okay, for the first 40 centimeters, but the remaining 20 centimeters was made as, okay, going to be shown as aliasing. So why did we get this aliasing here? Mainly because our Nyquist limit was lesser than the velocity of blood. Whereas, okay, yes, if we, for instance, okay, increase our Nyquist limit, so let's say, yes, okay, 70 centimeters per second. And okay, maybe, yes, okay, even down here, yes, okay, 70 centimeters per second. The velocity of blood was 60. Now, saying that, okay, we can say that, okay, now the Nyquist limit that is greater than the velocity of blood. And when we, yes, okay, record that 60 centimeters, okay, it's going to, yes, okay, even because it's okay, the limit of 60 goes here. So that's where we mainly can say it's okay that we don't, there is no ADAC. Mainly because, okay, our speed limit that we had said was 70 centimeters per second, where, okay, the velocity of blood was only 60 centimeters. Okay, so now we actually have, okay, we're going to take, okay, yes, a lot of points together. Because, okay, yeah, okay. that I said in the beginning. It's in pulse wave Doppler that we have aliasing. Now, every time we talked about pulse, that's okay, goes. Whenever you hear the word pulse, or we can say, okay, pulsed wave. Valve should be the next thing that comes to your mind.
Peer P and peer F.
Exactly. Now here you mean it says, okay, this PRF. What was that? The number of pulses per second. Now when we talked of, okay, yes, pulse wave Doppler, we said, okay, yes, if this was your blood vessel. Bar Chitavi. Bar where? Okay. This sample gate here. Well, okay, as we could move it to, let's say, as okay, to different depths if you wanted to. Right, okay. Right. But we also could say as okay that this depth here, the depth at which we kept the sample gate, mainly as okay, would determine the time that it would take the pulse travel to the gate and come back, travel to the gate and come back, travel to the gate and come back, travel to the gate and come back. Because that is actually it's okay based on how it's okay. This mechanism here is okay, will determine the Doppler shift frequency. Clear? Okay, Baby Khomeini says okay that okay, this PRF here actually is okay, will determine, we can say okay, or play a determinant part in the what we like call the sampling rate. Another point that we also said about is okay, your pulse wave Doppler, okay, yes, that its main negative point was that was going to have aliasing. And why do we have aliasing? Because the Nyquist limit is exceeded by, we can say it's okay, the speed. If you don't like speed, well, okay, it's okay, you can say the velocity of blood. So, ladies, what you will find in your book is an equation of as okay, how to determine the Nyquist limit. And that is made as okay, just going to be as okay, this PRF here. Divided by 2. Did you girls get that?
What does it say in the brown?
The brown? Because I
Yeah.
said, well, okay, why did we get aliasing? Mainly because your Nyquist limit is exceeded by the speed or velocity of blood. Just as we wrote here. There's nothing new. Or more correctly here. That if the speed of blood is greater than the Nyquist limit, we will have aliasing. Whereas, okay, if the Nyquist limit is greater than the velocity of blood, you will not have aliasing. And what did I say that the Nyquist limit was? Practically, as okay, if you look at a Doppler, it's going to be as okay, the maximum positive or the maximum negative speed that you're able to record on any setting. That would be considered as the Nyquist limit. Now, if your blood flows at a speed greater than that exceeding amount of speed, which is beyond your Nyquist limit, will become aliasing. That exceeding speed, or that speed that exceeds your Nyquist limit, is going to become aliasing. But what you mainly can okay, see from this formula here is that okay, a Nyquist limit is calculated by as okay, your PRF divided by 2. So let's say that okay, yes, your PRF was 4 hertz. Okay, that divided by 2 means okay, just give you okay as a Nyquist limit of 2 hertz. Did that make sense?
Yes, so it won't be able to exceed 2 hertz. That'll be the maximum limit.
Yes, but just keep in mind, my dear, okay, that this hertz here is okay. Now, although it's okay, that's a frequency, but what your system will do is translate that into a velocity.
Okay.
Okay, girls. Just take, you can say it's okay, a short 10-15 minutes break. Read on these 2 first pages of, okay, that's a 1.5 page of, okay, that's aliasing. And when we come back, we will, okay, yes, continue. Okay.
Okay.
Yes, girls. Welcome back. Any questions so far? So what you girls may realize is from this equation, let's just rewrite it so we have it now afresh. Black and white, that the Nyquist limit was equal to PRF divided by 2. Okay, so if you look at the equation here, it's okay, your PRF, that is numerator of the equation of your Nyquist limit, which mainly means that, okay, it will be directly proportional to your Nyquist limit. It mainly means that, okay, yes, increasing your PRF will increase the Nyquist limit, and or decreasing your PRF practically is going to be, okay, how will decrease the Nyquist limit. Now, girls, please keep in mind whenever, yes, okay, you turn on a Doppler function. Yeah, there was, okay, yes, spectral Doppler or color flow Doppler. Sem acquisition. Okay. The functions of these knobs here is going to change, or is going to be different than it used to be as, okay, in a regular B mode. Is that clear? So when we say Doppler mode, this knob over here is, okay, which in B mode mainly was going to be as, okay, we can say, okay, your focus position. And focus number. In Doppler is going to change to become, yes, okay, what we will call PRF. And another function that we'll talk about later on is going to be wall filter. So pretty much, okay, yes, the first knob on your right side of these 5 knobs, yes, okay, that we had right next to, yes, okay, that touch screen. We actually see, yes, okay, when we turn on Doppler, this knob here is going to, yes, okay, have 2 functions, which is going to be the PRF and the wall filter. So what we actually can say here is, okay, yes, if we turn this knob here clockwise, that is going to, yes, okay, increase your PRF, which is going to, yes, okay, increase your Nyquist limit. Whereas, okay, yes, if you turn it the other way around, anti-clockwise, that's going to decrease your Nyquist PRF, which will decrease the Nyquist limit. Okay. Did that make sense? So pretty much, okay, yes, by twisting and turning this button here clockwise, anti-clockwise, there will be a point where, okay, yes, where your aliasing may disappear. Clear? Mainly because, okay, the PRF increased to a limit where the Nyquist limit increased enough to be as, okay, equal or at least as, okay, faster than the velocity of blood. Or another way, that, okay, you just give me a second, guys. numbers. So where were we? That's okay. If you keep on, let's say it's okay, decreasing the PRF, you will reach a point where, okay, as you go from having no aliasing to have aliasing, mainly because you decrease the Nyquist limit to a limit where it's going to just, okay, be lesser than the velocity of blood. Is that clear? Now, please, 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 please keep in mind that it is the PRF and not frequency. That will be increased to increase the Nyquist limit and get rid of aliasing. Right, okay. But as we may, as okay, say later on, as okay, this Nyquist limit here, right, the Nyquist limit, mainly as okay, will also as okay be related to as okay what we call okay as a sampling rate. And we can mainly say it's okay by increasing the sampling rate, the Nyquist limit will increase, which may mean that okay, we'll be able to just okay record Doppler with less or no Doppler. Oh, sorry, aliasing, sorry. Okay. Any questions? Yes, girls.
No.
Okay. Now, ladies, the next topic. Okay, now your book talk says, okay, say about it, charts on aliasing. Oh, yes, okay. You say charts, that's okay. That's thinking about it. It's not real. Okay. It's okay. What this whole thing is, okay, what this next topic about, okay, charts on aliasing is going to be about is how to get rid of aliasing. Because, ladies, he had a Doppler shift. With aliasing. Now, what are the 5 possible steps that we can take to get rid of this aliasing? And say, well, okay, if you only had, let's say, it's okay, a positive Doppler shift, how do we get that positive Doppler shift recording with no aliasing? Or, for instance, yes, okay, if you had a negative Doppler shift, Right, okay. Yeah, that was aliasing. How are we going to be able to just record that negative Doppler shift without aliasing? Did you guys get that? Okay, so there are mainly going to be 5 basic steps. Now the order in which the book has written it versus the order that I will go in is going to be a little bit different. Okay. But practically speaking, we can say this will be the order in which you will be taking your steps. Now the first is going to be we can say increasing the scale. Okay, now we're going to just talk a little bit in advance, in details about this one here. The next step that we can take is a baseline shift. Now we can say we may also go in a little bit detail about this one here. We can say the next step is reduce the transducer's frequency. And to understand how that is going to help us get rid of aliasing, just remember your Doppler shift equation. We then can say another step that can be taken is reduce the depth. And last but not the least is going to be use a continuous wave Doppler. So these are 1, 2, 3, 4, 5 steps that can be carried out, which if this doesn't, then yes, this will do it. If this doesn't, well, yes, using a shallower, lower transducer frequency will do it. If that doesn't do it, scan at a shallower depth. And if all of these steps here doesn't get rid of aliasing, then the last step is just use a continuous wave Doppler, because that is going to be free from aliasing. Why? Because aliasing was only seen in pulse wave Doppler. Is that clear? Is that clear, Gauss?
Yes.
Good. Now, let us just take up the first step. If you mean yes, now how do we get rid of aliasing? We can say it's by increasing the scale. Is that clear? Now, ladies, although yes, okay, the book here is okay, word uses the word scale. But what is it that we practically, yes, okay, are going to be increases? Oopsie. That PRF. And we know that, okay, as that increasing that PRF, what going to practically is okay going to do is that was going to increase your Nyquist limit, right? Right?
Right.
And you can say it's okay, the more you increase the Nyquist limit, okay, because what was it that we said that the Nyquist limit was? Mainly as okay, just a numerical value of okay as the maximum speed that you're going to be able to record. So if you increase that, yes, okay, what you will have is, well, okay, yes, you are going to be able to, yes, okay, record higher and higher velocities of blood without seeing aliasing. So that's how you get rid of aliasing, right? So practically, yes, okay, this increasing of the scale as mean as okay, just going to be as okay by increasing your PRF. How do we do that? Well, okay, yes, those 5 knobs here. This knob here is okay. In a Doppler mode has okay as the function of that the PRF can be adjusted, which is mean that's okay, just going to just okay increase the Nyquist limit. So what would that mean? Let's say it's okay that we start a Doppler recording. Okay. Now let's just, for instance, say that okay, as we have a positive Doppler shift. Okay, which mainly mean that okay, as what our graph ideally is okay, actually is okay, going to be C would be is okay on this side of your zero Doppler shift, or what we also call the baseline. But let's just say that okay, yes, our velocity here was 50 centimeters per second. Whereas at this point here is okay, our Nyquist limit was set as a speed of 40 centimeters per second. Did that make sense? So we can mainly say, okay, our first 40 centimeters, well, okay, there was no problem with that. It was mainly as okay, just the last 10 centimeters. That was a problem, which was going to just okay be. We can say it's okay, just break down here. And that was your ADs. Now, what we're practically as okay, we'll just do in this case here is what okay, yes, our PRF button or knob. We will increase it. How do we increase it? Turn it clockwise. And what you actually just okay will see is that okay, now physically goes just okay, the size of your scale remains the same. We still have, okay, as our baseline here. Right? But we may say that, okay, yes, it goes from, as okay, from line to line, is okay. Okay, this is still okay as our zero Doppler shift. But instead of, okay, going by the counts of 10 in Mega, let's say, it's okay, just say, it's okay, it goes now by the counts of 20. Likewise here. Minus 20. Minus 40. Minus 60. And let's see, it's okay, minus 80. Now your velocity of the blood has not changed. It is still, yes, okay, 50 centimeters per second. Positive Doppler shift. So what happened? That graph is, first of all, as okay, was so big that it would not fit. We can say it's okay within the frame. At aliasing, which I showed at the negative side. But now, yes, okay, two things will happen. This graph is just going to be like this. Or maybe it's a little bit too much. Mainly as okay, because it's okay. Or we mainly just did what he said, like if 40 is too low, we increased it to 50, to 80. Even if you just increased it to 60, yes, okay, you still have had, or yes, okay, Doppler shift without aliasing. Did that make sense? Did that make sense, girls? So pretty much okay, yes, by just yes, okay, increasing your PRF, you actually just okay end up yes, okay, increasing your Nyquist limit, which then in this case is okay, after you have okay, increasing the scale. Did you girls get that?
Yeah.
So we can say as okay, now this thing here has it has an advantage, it has a disadvantage. We can mainly say that okay, yes, the advantage of okay, yes, increasing the scale is okay, yes, okay, we get rid of aliasing. Did that make sense? Did you girls get that?
Yes.
Clear? Now here we can say it's okay, in this example, it's okay with me, it's okay, just went from A to B, it's okay, we just, let's say it's okay, doubled the scale. Clear? Let's just say that, okay, yes. Now what if we, for instance, okay, went on and okay, has kept on, let's say it's okay, increasing the scale from it's okay, not double it, but actually that's okay, increase it 10 times. This is still your zero Doppler shift. But this here will now be as okay a velocity of 100 centimeters per second. This will be 200 centimeters per second. This will be 300 centimeters per second. And we can say as okay, the Nyquist limit, yes, okay, now will be as okay, 400 centimeters per second. Now we said, ladies, well, okay, the velocity of blood was still, there's okay, a positive Doppler shift of 50 centimeters per second. Now, if you look at that, just okay, that graph is going to be like this. Because we can mainly say, okay, that this level here, sorry, that is 100. Your 50 centimeters is going to be, it's okay like this. It's going to be somewhere here. So as okay, a negative point, we can say it's okay, a disadvantage of increasing the scale is that okay, yes, that it becomes, that our scale here is okay, becomes less sensitive to low Doppler shifts. Did that make sense? So you can say it's okay, increasing the scale is good, but increasing it too much is going to be bad. Because okay, as you may say, as okay, in this blood vessel here is okay, you had a Doppler shift of 50 centimeters per second or speed. There might be as okay a neighboring blood vessel where okay, yes, where the speed was lower. Let's say as okay, 10 centimeters per second. And this 10 centimeters per second actually that's okay will be as okay considered so low now here that actually that's okay will be recorded as a zero Doppler shift. Because goal is okay, here I'm just giving you the example of spectral Doppler. But you still got it, okay, think about this, it's okay, what about color Doppler? As well. Verifies yes, okay. If we had a Doppler shift, let's say it's okay. In this case, it's okay, where okay, yes, this yellow up here was 40 centimeters. And this here is okay, was minus 40. Then you mainly say that okay, as your blood vessel that you had is okay, will have mainly yellow, but it's okay, you also have okay, as areas of orange. Yeah, this orange here is okay, that was going to be it's okay, your areas. But likewise, it's okay when you increase the scale from let's say it's okay, max 40, minus 40, shoot 80s, 80s. Then we can mean it says, okay, this yellow here will go from 40 to 80. This orange here will go from 40 to minus 80. Okay. Where you then can say, okay, well, the color within the blur vessel is okay, may change because it's falling in the range of this. So yes, okay, it may become red. But if you increase it so far that, okay, yes, it goes by hundreds, then you can say that this color here is okay, will be your 100. This will be as okay from 100 to 200. Next, here will be from yes, okay, 200 to 300. And this will be as okay, become as okay, up to 400. Okay, which to begin with, as okay, was recorded as okay, yes, a maximum of 40 with aliasing. Well, okay, we got rid of the aliasing because we increased it to 80. And so on. So the same as okay applies for as okay for your color scale or for your color Doppler. Okay. But as okay, you increase the scale, and that's mean as okay, what they say is okay, you increase the scale. Practically as okay, how is it if we do it? We mean it's okay, just increase our PRF. The plus point is that okay, that's going to be as okay, probably as okay, one of the easiest way by which we as okay, because says okay, increase our Nyquist limit. Because it's going to directly as okay say, well, okay, as okay, before we were only able to as okay record up to 40 centimeters per second. Now as okay, we are equipped with new scanners or new scanning guns. The police and okay, now we're able to as okay record up to 80. That may not be strong enough for us okay drivers like Shaq. So that's why okay as they increase as okay up to these. Okay. But as okay, as we increase the scale, it's going to become less and less and less and less and less and less sensitive to low Doppler shift velocities. I'll just take an example of okay, as your kitchen scale versus your bedroom scale. Now some of you say, Mike, what do you mean by a scale? Well, okay, yes, the thing that you weigh things on. Now your kitchen scale is mainly as okay, only we can say it's okay, it has a max limit of let's say weighing up to just okay 5 pounds. Did that make sense? Now, if you put, let's say, as okay, 10 pounds worth of okay, as anything on that, it can only show you up to 5 pounds. Clear? So that remaining 5 pounds that is exceeded is going to be as okay aliasing here. But you take that okay as 10 pounds onto a bathroom scale, which is able to, you can say it's okay, measure up to, let's say it's okay, 500 pounds. Okay. The distance of okay, yes, of the movement of that pointer is going to be lesser. Whereas if you not take yes, okay, that substance that okay, put on a scale that they use in okay, seaports and so on, so which are going to be as okay, measured and okay as several thousand pounds. Well, okay, yes, that scale may not even respond to it. Say, okay, this weight here is too low for me to detect. Did that make sense? So putting as okay, a packet of grapes on okay as on your bedroom scale is not going to show much compared to as okay what it will show on a kitchen scale. Clear? Okay. Because the numbers that you have, you mainly as okay will see okay as you increase your PRF. Or what we mean is okay, just say as okay, increase of the scale. You will see that okay, first these numbers yes okay may go by tens. Then they may go as okay be counted by hundreds. And so on. Okay. So yes, okay, if a scale first was like this, 10, 20, 10, 20, 30, for instance, and we increase it. Well, okay, the size of the scale is the same. It doesn't change, but now it's okay, it may go, let's say 50, 100, 150. So yes, okay, a scale that for instance, okay, before was like this. We can say, okay, this was exceeding because our upper limit was 30. We can say, yes, okay, it was 50. Now here, yes, okay, that 50 is just going to be shown like this. So you can maybe say, okay, that the size of the graph actually is okay, is smaller. Where, okay, if you further increased it to, let's say, as okay, just hundreds. It's still 0. This will be 100. This will be 200. Now this will be 300. That graph, which was okay, now was shown like this, is going to just okay be even physically small. Because your scale gets less and less sensitive to yes, okay, low velocities. Well, okay, we can say okay, the velocity is okay to beginning in the beginning here is okay, it was low because we had set it okay as at a max of 30. But when we increase the scale, yes, okay, that graph that used to be big became smaller. We increase the scale even further, even that okay, that smaller graph is going to become even smaller. And some of you will say, so what is the disadvantage about that? The disadvantage here is that okay, yes, your system will be lesser and lesser likely able to record velocities in blood vessels where the velocity is low. Did that make sense? Did that make any sense?
Yes.
Okay. Anybody who didn't get it? Okay, ladies. So if you got it, you got it. Have I made myself clear? So the reason that we say it's okay, increasing the PRF has a disadvantage, which is reduced sensitivity to low Doppler shifts, is because in case of low Doppler shifts, may not be able to record it. And that is going to be obvious when we look at image where we have a color Doppler. Where we might have had two blood vessels. Because there was one with the high velocity and a neighboring one with a low velocity. And this fellow up here is with a high velocity, he would show aliasing. And just this is the extreme negative. And we can just say it's this might be the extreme positive. Where we say we may say aliasing in this blood vessel here. This one here was a low negative velocity. Now when we increase the scale, this top vessel here will get rid of the aliasing. This bottom vessel here may become lesser and lesser filled with color. Or actually if you keep on further increasing the PRF. This top vessel may become lesser filled as well, and the bottom vessel may actually become completely emptied out. So we can say we increased the scale too much. Because now it increased to a level that it was not going to be able to record these low Doppler shift velocities here. And they actually will be mimicked as or represented as a zero Doppler shift. You girls got that? So
Yeah.
so just keep that in mind. That's one of the main disadvantages of increasing your scale. Okay. Now the next step that you can do to get rid of aliasing is what we mean is, okay, this can call it, okay, a baseline shift. Now, girls, please keep in mind that, okay, yes, it is not only in a spectrum where we had a baseline. And we already know that, okay, this baseline here is, okay, represents, okay, as a 0 Doppler shift. We also, as okay, had a baseline. If you chart color map. Did that make sense? Whereas per standard, yes, okay, we know that, okay, yes, unless until we switch or invert the spectrum or invert your color map, whatever is above the positive line, whichever is above the baseline is positive Doppler shift. Whatever is okay as below the baseline is going to be as okay negative Doppler shift. Now it's easier as okay to just demonstrate it as okay on a spectral Doppler, because this was your baseline, which we know represents the 0 Doppler shift. So we call that the baseline. Now let's just say, for example, that okay, yes, I hope everybody will know what this is going to be. It's okay, this is your Nyquist limit. Or we can say, okay, the Nyquist limit of your positive Doppler shift. This here is going to be, it's okay, your Nyquist limit of the negative Doppler shift. Is that clear? Now let's just say that we had, okay, as a positive Doppler shift. With, okay, as some alias. Mainly is okay because in this case it's okay we were missing this part here. Why were we missing this part? Because okay, it's going to be shown as aliasing down here. Clear? So this fellow here is okay, that is your aliasing. We actually, that's okay, should have been on top of this graph here, but actually it's okay, it's decapitated and shown down here. Where we mainly can say is okay, this point here is okay, our readings may go, let's say it's okay that it goes by 100, for instance, 200, 300, and let's say it's okay. It's going to be, it's okay, 400 centimeters. Now, right now, it's okay, we can say it's okay that the baseline is what we call is okay at 50%. Which means that okay, as your negative Nyquist limit is going to be as okay, minus 100, minus 200, minus 300, and we can say, okay, the Nyquist limit here is okay, will be minus 400. So what we actually as okay will do when we see as okay a baseline shift. In this case, as okay, we will actually as okay move the baseline down. Clear? In this instance, yes, okay, we will actually as okay move the baseline down. So what you actually will see is that okay, as your baseline is going to be like this. And you'll see that okay, this will go to yes, okay, still minus 100 because it's okay, minus 200. We're up here. This will be 100, 200, 300, 400, 500, and we can say it's okay, even 600. Where we say it's okay, in this instance, okay, here our Doppler shift, for instance, okay, was 500 centimeters per second. But where our Nyquist limit was, okay, yes, on the positive side was only 400 centimeters, and so on the negative side. So by bringing the baseline down, that's okay, what happens? That 500 centimeter now is in, okay, yes, your Nyquist limit. Clear? Because we didn't really need, okay, yes, a Nyquist limit on the negative side to be as okay, 400 centimeters. Did that make sense? So mainly as okay, just by yes, okay, moving the baseline down. Or it's okay, in this case, as okay, do a baseline shift. The scale limits, okay, as okay, the total of your okay scale okay still remain the same. It was still going to be able to okay only measure 400 on the negative side, 400 negative, positive, by a total of 800 centimeters per second. But we made it okay, just move the basement down. So that's okay, that now I was able to measure up to 600 on the positive side, and okay, just 200 on the negative side. We didn't really need that much on the negative side because, well, okay. Our main issue was okay, as of a high positive Doppler shift. Now you can mainly as okay, so some of you may say, okay, so is that only possible if we had a positive Doppler shift with aliasing? No. The same just applies as okay, even if you, for instance, okay, had a negative Doppler shift. And let's say some aliasing. And we could still say about okay, yes, our speed limit was there, yes, okay, it's 400 centimeters. Where okay, yes, the velocity of blur was 500 centimeters per second. The only thing that's going to be different here is okay, that because in the first case, okay, we actually has okay, brought the baseline down. In this case, what we're going to be doing is we're just going to move the baseline up. And when we do that, what we actually will see is that, okay, this is still our spectrum. Right? But we move the baseline up. This becomes, yes, okay, the new zero Doppler shift. Where it says, okay, here, 200. And let's say 200, and then we got, okay, yes, 100, 200, 300, 400, 500. And let's say it's okay, 600. So that graph, or that's okay, that reading where we first had a negative double shift with aliasing. Well, okay, yes, now that graph is going to, yes, okay, be kind of whole solid off, yes, okay, measuring. Or be able to measure, yes, okay, at 500 centimeters per second of velocity of blood. Did that make sense? Did that make sense, girls?
Yeah.
Right, okay. So the whole point here mainly was, okay, yes, we had a graph of a velocity of a Doppler shift. It doesn't fit in the frame. What can we do? Okay, the first was, okay, yes, increase the size of the frame. Well, okay, by increasing the scale. By the second step was, okay, that we could actually, okay, shift the baseline. And so, okay, if we move the baseline down, we just place 0 Doppler shift at a new location. And so, okay, from here, it's okay, that's when you go and count our positive Doppler shift. Of course, yes, okay, it's going to just, okay, increase our, yes, okay, ability of increase, yes, okay, recording higher and higher positive Doppler shifts. But that was the one that was causing us problem because it's giving us aliasing. So we got rid of aliasing by doing so. Likewise, that's okay. We can raise the positive, or we can raise the baseline up because we had a negative Doppler shift, which was giving us problem because it was at a speed greater than our negative Doppler shift. So me is okay by raising the baseline, which is just going to be again, which is shifting the baseline. The speeds or the velocities that we were able to just okay measure on the negative side has increased until yes, okay, the level that okay, yes, we didn't have any aliasing anymore. Did you guys get that?
Question. I have a question. So
Okay,
when you
check.
Oh.
Do you mind if I just talk of one point and then you can ask a question, dear?
Yes, go ahead.
Because let's say that, okay, yes, this was our scale. Okay, let's say that, okay, the max here was, you can say it's okay, minus 600. And okay, yes, on the positive side, okay, it was 600. Now your question may be, yes, okay, Mike, will we be able to, yes, okay, move the baseline all the way up here? This becomes, yes, okay, your new baseline. And okay, yes, then what is going to be, yes, okay, our max positive negative Doppler shift? It's just going to be 1200 because this 600 and this 600. Or on the other side, can we bring the baseline all the way down here? So this becomes, yes, okay, our new baseline. And okay, yes, then this is income, yes, okay, plus 1200. Did that make sense? Clear? But if your scale, yes, okay, here was low, we can say, okay, minus 300, and okay, yes. Even if you brought the scale, yes, okay, baseline all the way up here, this will only have been a total of 600. Or even if you brought the baseline all the way down, this was still less than being okay, it's 600. So things like that. How can we increase these numbers? We can actually just increase them from 300 to 600. Just from 300 to let's say 600. By us increasing the PRF. Did that make sense? Did that make sense?
Yes.
Okay, Vashak, what was your question there?
I was just trying to clarify. So when you move the baseline
Mhm.
down or up, it's basically canceling out the aliasing because it's no longer the velocity of speed is no longer more than the sample rate.
No, not your sample rate, my dear.
Or the, what is it called?
No.
The Nyquist?
Well, not really.
Okay.
Okay, because we already let's say Now, what happens when you increase your Nyquist limit? That's the difference between the two. Okay, we said here's we went by chance. Increase the Nyquist limit so it goes by hundreds. Yeah. So that was increasing the PRF, that is how we increased the Nyquist limit. But right now, your baseline is still in the middle. So it's what you had positive here is going to have an equal, but just negative. Yeah. Yeah, where you go and say, well, this is going to be minus 100, minus 200, minus 300, and minus 400. Clear? That was by increasing your PRF. Now, my idea, what you can do here is in this case here is you can do a baseline shift. Even in this one here, and we can say even here is if you do a baseline shift. Let's just say that we bring the baseline down. Let's say we bring it down like this. This would just be minus 10. This is your new 0. So this will become 10, 20, 30, 40, 50, 60, and 70. Did that make sense? Whereas this here was that's where you had as your Nyquist limit to 400 minus 400. And as let's say we do a similar as baseline shift, just bringing the baseline down. Well, yes, this will become your new baseline, which will be 0. Because that's we can record up to minus 100. And this will be 100, 200, 300, 400, 500, 600. And you can see it's okay, 700. Did that make sense?
Yes.
Okay. So if it only as okay, you can say okay, increase as okay your scale on the positive side. But it's okay, there's going to be an equal decrease on the negative side when you do a baseline shift. That doesn't happen when you just okay increase the scale. Because as you increase the scale, it go from yes, okay, they're going to equal change on both sides. Did that make sense?
No, can you go over the last, so if, when you increase,
Because when you increase the scale, my dear, you said, okay, here was 10, 20, 30, 40. Minus 10, minus 30, minus 30, minus 10, minus 20, minus 30, minus 40. You increase the scale, right?
yes,
So what's going to happen? Okay, let's say it's okay, increase it 10 times. So that's okay. It goes 100, 200, 300, 400 on the positive side, minus 100, minus 200, minus 300, minus 400 on the negative side. Did that make sense?
yes, that do.
Okay.
My question is, when you shifting it down, it's not gonna be the same, it's not gonna go from 10 to 70 on the negative side?
No.
Okay,
Because your total scale was, let's say it's okay, if you had a total scale of, let's say it's okay, measuring 80, right? Right?
Yeah.
Because 40 plus 40 is 80. That's
okay,
why I say it's okay if he is okay, just in this case, it's okay, move the baseline down. Because okay, now this here, this point has okay, that became yes, okay, your new zero Doppler shift or new application of the baseline. But I may have okay, just kept okay, as because okay, you're still going to be able to just okay measure up to minus 10 centimeters positive, negative Doppler shift, right? Okay. But where you saw on the positive side, okay, it went from it just okay, it went from 40 to 70. But okay, you had less okay negative Doppler shift. But if this was your scale that you had set, and you did a similar yes, okay, baseline shift, well, okay, because otherwise it would have been yes, okay, 400 plus, 400 minus. As long as your positive velocity and negative velocities were within these limits here, you were good. But if you had, okay, what we mainly what I said here is, okay, we had a positive Doppler shift that was giving us problems because we could only measure up to 400 Doppler shift of 400 centimeters per second on the positive side, which was giving us aliasing. So we could just, okay, bring the, yes, okay, baseline down. Now with this at the same scale, yes, okay, your total was 800, right? Clear? So by bringing us, okay, the scale, as okay, baseline down to the same degree as you had over here, it's going to, okay, we are able to measure up just, okay, 100 centimeters of 100 centimeters per second of as a negative velocity. But as okay, our positive velocity, as okay, we are able to measure up to 70 centimeters, 700 centimeters per second. Did you get that?
Yes.
So, okay. Now, some of you will now ask me, Mike, how do we move the baseline? That's why I say it's okay. The theory of, okay, yes, ultrasound physics, that's the hard part. The practical is very straightforward. Because, yes, okay, goes of your 5 knobs here. Now, we already said this one here is okay. In Doppler, that was okay as your PRF. And or as okay, wall filter. We talk about wall filter probably tomorrow. But then you see it's okay that okay, whenever we had it's okay Doppler mode. I think it's this knob here. If not, it's this one here. But that's going to just okay, say baseline. So my girls, if you yes okay turn that anti-clockwise. Oh sorry, clockwise. That is just going to just okay move the baseline down. Whereas if you turn it clockwise, it's just going to yes okay move the baseline up. Now, usually it's okay, whenever it's okay, you start the system, you may say it's okay, you may see that okay, it says 50%. Now, what does that 50% mean? It means that okay, yes, it is right in the middle. Where you mainly see that okay, yes, the maximum here, let's say it's okay, if that was 30. This is going to be 30 as well. You can increase this number. Or okay, yes, you can increase all of the numbers. By me, it's okay, increasing the scale. But once yes, okay, start yes, okay, moving the baseline up. Oh, yes, okay, once you start moving, yes, okay, the baseline down. You may, yes, okay, just set a new level for your 0. And then we'll say, okay, this then will just become, yes, okay, it's not going to be 30 anymore, it may be just come 10. And then you say, okay, yes, a new 10, 20, 30, 40, and 60, or 50. Did that make sense? Or if you, yes, okay, bring the baseline up. You can say, okay, we brought the baseline up. Now this does become just okay, the new 0 Doppler shift. Where we can say as okay, this would just be 10. Then we go a new 10 here, 20, 30, 40, 50. But if this was not 30 and 30, but let's say as okay, 60 and 60. Because okay, this will still have been the new 0, this will still have been the new 10. But then this one here will become just okay, 110. And so on. But it does not increase the scale because increasing the scale is going to increase on both sides. baseline shift, you just shift the baseline to a new location on the scale. Or set the bar higher or lower. Does that make sense? Any question, ladies? So yes, okay, you can take your sheet of paper out and you will see that, okay, there's where it says, okay, PRF in both Dopplers, right? You can see it's okay, baseline in both Doppler modes. It's just a matter of, okay, yes, increasing the scale for the PRF. And it's okay doing a baseline shift. Okay, so practically it's okay, the knobs are right there. You just have to be able to just, okay, turn that knob clockwise or anti-clockwise. Any question, girls? Okay. Damn it. Okay. Now although not directly as okay mentioned here, but we can say it's okay. Although directly as okay, it says there's no disadvantage of, okay, yes, reducing your transducer's frequency. But practically as okay, there is because, well, okay, can't be used for color Doppler. So yes, okay, if you're having aliasing and a color Doppler, reducing your transducer frequency is not going to be as okay an ideal method of, you can see as okay getting rid of aliasing. Did that make probably not net, but just keep that in mind, okay, girls? Now your book uses the word sorry. Yes. Now all the SOK is mentioned in option 2. But yes, okay, may do it here. You can also ask, okay, wouldn't it be better to do that before going to yes, okay, a lower frequency transducer? Yes, you can put it that way. But it's okay, it's just option 2, which means it's going to be as okay, use or we can say okay, select. Okay, that's fine. New ultrasound view, okay. With shallower depth. Oh yes, okay, use the word sample volume. Now what does that mean? Now goes, look here. Let's say it's okay, this is the depth through which is okay, you're scanning. Let's say that in this point here is okay, we have the transducer. Let's say this area here. Okay. Now go, the reason that we is okay, it use the word is okay is sample volume. Is because okay, we still are okay as talking now okay as a pulsed wave, or yes, okay, using a pulse wave transducer in a pulse wave Doppler mode. Because it's only going to be in this that we have aliasing. Now just keep in mind, ladies, okay, let's put it this way. That okay, I said this depth here is okay, mainly it's okay due to the angle from which we are scanning. The blood vessel here is okay as at a great depth. That will mainly mean that okay, yes, we actually yes, okay will have to keep yes, okay, the sample window at a great depth. Okay. Did that make sense? Which mainly would mean that in this case, yes, okay, what is it that we will have? Indirectly, yes, okay, we will have a greater PRP. Because what this sample window here actually is, okay, that's going to be, okay, we can say, okay, the depth to which the pulse will travel to, and of course, yes, okay, come back. Before, yes, okay, another pulse can be sent out. Did that make sense? So by, yes, okay, having a greater PRP, what was going to happen? You have a lesser PRF, right?
Right.
And what is it that we already know that this lesser PRF is going to be doing? Well, okay, maybe yes, okay, indirectly yes, okay. Or practically yes, okay, scanning wise, okay, guys, okay, have a lower Nyquist limit, which may recall that okay, there's going to be a greater likelihood of aliasing. Okay, but here, ladies, is okay, we are not turning any knobs on our keyboard to fix this. But what we mainly say is, okay, this is still this blood vessel here, is okay, which is all dependent upon, is okay, the angle from which we scan it at. Yes, okay, that's going to be, yes, okay, a great distance between the transducer and the blood vessel. Did that make sense? So what, okay, yes, okay, it's okay, selecting a new view of ultrasound view with a shallow depth. Mainly mean that you actually, yes, okay, physically, yes, okay, may have to, yes, okay, move the transducer to an area where you actually, yes, okay, still will be, yes, okay, you can say, yes, okay, sending pulses on to, yes, okay, this relevant blood vessel here, but where the distance between your transducer and your, what you want to call it, blood vessel is going to be lesser. Clear, which means, yes, okay, then will cause that, okay, yes, at a shallow depth. What is it that we will have? We will have, okay, yes, a greater, yes, okay, sample rate. Why? Mainly because, yes, okay, because of the lesser distance then now is okay, this is a shorter PRP. Which mainly is okay, will directly lead to is okay that the PRF is increased. Okay. And okay, as we'll call it, okay, as the Nyquist limit will be increased. And by doing so, yes, okay, mainly as a because of our sample window here, not the depth of your image, not by the depth of your image, but it's okay for your sample window. It's okay, you will have less aliasing, or you get rid of aliasing. Let's just take an example. Let's say you want to scan this carotid here on this side. Or you can place your transducer like this. But what do you see? First, it has to pass through my trachea to get you okay to the carotid artery over here, right? Which is going to be a great distance. Did that make sense? Well, that would be a dumb thing to do, but anyways, just okay, give an example. So what do you have? A greater PRP, you will have a lesser PRF. And a lesser PRF is going to cause, okay, as you will have lesser count, is okay, you can say it's okay, your counting of samples per minute, per second, sorry, is going to be low. Okay, where you mainly can say is okay, this is where you mainly can say is okay, that your sampling rate is going to be as okay, lesser than the velocity of blood. Yeah, okay, as you want to scan it here, this one, here, right here. That's at a shallower view. Did that make sense? So mainly as okay, if you are having as okay liaising, scan the blood vessel from an angle or from a view where you actually, that's okay, where there's going to be as okay, a lesser distance between your transducer and the relevant blood vessel. Because when the distance is greater, you will have greater time interval between your counting. Versus if the distance is shorter, you'll be able to count faster. Did that make any sense? So again, yes, okay, it comes back to yes, okay, where we were in the beginning, when we start talking releasing. That okay, yes, if your sample rate, and that's why yes, okay, we use the word sample rate at that time, is lesser than the velocity of blood, that will lead to aliasing. Clear? What will be aliasing here? We can say yes, okay, if I'm given the task to yes, okay, count the cars that runs on the street. And the cars go zoom, 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 like that. But my counting is like 1, 2, 3, 4. Now between 1 and 2, there's going to be zoom, 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 cars moving. Between 2 and 3, zoom, 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 cars moving. That okay, yes. Cars that I miss between 1 and 2, 2 and 3, 3 and 4, 4 and 5 is going to yes, okay, become aliasing. Clear? But if the car go like zoom, 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 and I'm able to try and count 1, 2, 3, 4, 5, 6, 7, 8, like that. Mainly because the time between each pulse going and coming, going and coming, going, coming is lesser. Then, okay, yes, I will not have any releasing. Or we can say at least the likelihood of it is going to be reduced. Did that make sense? Okay, so goals. Here, yes, okay, this doesn't mean, yes, okay, your view of depth. You can still have, okay, yes, let's say it's okay, image view of, let's say it's okay, 10 centimeters. But it's okay, if you say that, okay, yes, here the distance, if this is your blood vessel, let's just say that, okay, yes, this is at a depth of, let's see, 7 centimeters. Okay, and it's a pulse width Doppler, yes, okay, this is your sample gate. It's going to be, it's okay, this PRP here, but this single pulse going back and forth. Okay, that is going to, yes, okay, determine, yes, okay, you can say it's your Doppler shift. Okay, now you can still have, yes, okay, your image view at the same, yes, okay, 10 centimeters. But yes, okay, if you scan the very same blood vessel, but just, okay, at a shallower depth. Let's see. It will be here. 3 centimeters. You move your transducer. And by doing so, yes, okay, you reduce the distance between the transducer and, okay, yes, the blood vessel. And please keep in mind, yes, okay, for you to be able to, yes, okay, to measure, yes, okay, the velocity or the, yes, okay, the blood flow in this blood vessel here, yes, okay. The sample window got to be, yes, okay, inside the blood vessel. Did that make sense? But mainly here, it's okay, because it's okay of a lower depth. We can say, okay, the PRF for, okay, as for this sample window here is going to be increased. And reduce releasing. Is that clear? Okay, so no matter what, yes, okay, if it is a deep depth, please keep in mind, ladies, you will only get a Doppler shift if the sample window is within the vessel. If the blood vessel is at a depth of 7 centimeters and you keep, that's okay, your sample window at a 3 centimeter depth. Well, okay, forget about no aliasing or aliasing. You will have no Doppler shift at all. Is that clear?
Yes.
Good. Okay, so what this step here actually may require, you can see it's okay, it's going to be it's okay, a slide. Physical manuring of your transducer. Did that make sense? So really not okay, something that you actually is okay will be able to okay do with your aliasing by okay touching keys and so on, so on, so. Well, okay, you can say that's okay. If you bring it to a shallow depth, you probably as okay may have to move the pulse gate a little bit as well. Right, okay. But the main manuring is going to as okay be by as okay manuring your transducers so that actually you are looking at the pulse. Oh, sorry, not a pulse, sorry, at the blood vessel at a shallower depth. Or you can make this okay, so that the distance between yes, okay, your transducer and the blood vessel is reduced. So that's okay. Did you ladies get that? So for this one here, you could pretty much, okay, just copy and paste your relationship to the depth with PRF and or PRP. But then just keep in mind that, okay, the greater your PRF, greater Nyquist limit. Greater Nyquist limit. Well, okay, the greater your Nyquist limit, less likelihood of aliasing. Any doubts? Now, ladies, the last thought. The last thought on aliasing was use a continuous wave Doppler. And the reason for that was that, okay, as if all of the 5 or 4 previous steps didn't get rid of the aliasing, we could mainly as, okay, the only option that we had left is, okay, as going to be as, okay, use something which is free from aliasing. And the one that was free from aliasing was as, okay, your continuous wave Doppler. You can mainly say it's okay because it was okay as recording or able to record very, very, very high velocities. Right? Which we said was okay as anything between is okay 8 to 9 meters per second. If that makes sense. So actually it's okay, go from pulsed wave Doppler mode to the continuous wave Doppler. Because pulse wave Doppler is okay, that's mean it's okay where we will see aliasing. First, because okay, it has very low velocities. But it's okay, even though we had okay as pulse wave Doppler, okay, we could still get rid of aliasing. Primarily as okay by increasing the best okay scale. We could do that by as okay increasing the PRF. We could do a baseline shift, even though it's okay having or using a pulse wave Doppler, and then get rid of aliasing. We could even as okay do as I just say as okay shift, or it's okay, scan the vessel from a shallower depth of view. Which means it's okay, will just cause us to just okay use what will give us okay as a greater sampling rate due to is okay greater PRF due to a lower PRP because of a lower depth, for which we send the pulse that was going to just okay record our Doppler shift in the pulse wave Doppler. And yes, okay, use a transducer, still a pulse wave transducer, but where that transducer had a lower frequency than we used before. So if these 4 steps here is okay, didn't do it, then the only option that we then will have left is going to be as okay to use a continuous wave Doppler. There was not going to be a pulse, but there was going to be as okay that area of overlap in which it's okay the Doppler shift will be measured, calculated. Mainly it's okay dependent upon it's okay the difference between the transmitted frequency, which was continuous, and the reflected frequency. The difference between these two here was going to just okay be determined in this area of overlap. Okay, but we still can say, okay, the greater the difference between the two will mainly mean that, okay, as the blood flows at a greater speed on an average. Oh, yes, okay. This whole area of overlap. Because its main disadvantage was that, okay, yes, not site specific. But I was able to just okay record up to high velocities without aliasing. So that was its main advantage. That we got rid of aliasing. Yes, girls. So how is Doppler going? Now, till now, anybody has any questions?
What do you think about the chart on page 323? Is that a good thing to remember? For like,
323. Every chart is good.
I mean, for like as a summary for what we just learned.
Yeah. Exactly. Okay. But that's just a summary. You also have to think of, okay, advantages, disadvantages. Okay. And a major disadvantage is when you, for instance, okay, increase the PRF. When we say increasing PRF, what we mainly meant here was, okay, it's increasing the scale. Because ladies, that's what you're going to just come across, and as a lot of questions in chapter number 20. That as we increase the scale, we increase the scale, we increase the scale, whatever happens. Or we may do what is the other function of the knob here. Or increasing the scale, which is the wall filter. Okay. Now, girls, for tomorrow's topics, which is going to be the remaining of chapter number 19. So we have some smaller topics, left. Now there's something that I would like you girls, make sure that you revise, look at, which is going to be your linear sequential array. Clear? Okay. Please look at reject. You remember reject? Right. And yeah. Please make sure that that you have looked at those. Please also make sure that you know the relationship between power, intensity, and amplitude. Well, it's probably too late to start revising on that one, if that should be something that you should be dreaming about. Now, whether you call those dreams sweet dreams or nightmares, that's that's going to be an individual story. Okay. So, okay, girls. So how is Doppler going?
There's a lot of information. A lot of information.
Okay.
He's got to do more studying because it relates back to previous chapters. That's just trying to make that correlation.
Exactly. But once you got that, yes, that's when it clicks.
Yes.
Right. Okay, go. So yes, well, as I said, and as I will say, and as I will keep on saying, it's please do not confuse PRP with period. Please do not confuse PRF with frequency. Clear? Right. Well, you don't have to remember as equations as on top of your head. But yes, the main thing that that will be important is you can say relationships. Okay. But if you remember an equation, you remember the equation and you remember the relationship. Okay. Because if you only remember the relationship, you only remember the relationship. You don't necessarily get the equation. And there are equations that you will need to know. Okay. Anybody have a question from an older chapter? Something they came across during the weekend that they want to clarify?
I have a question.
Yes, my dear.
The question that you always ask about the backing material, I always say vibrations or like absorption of like the pulses. Like, and then you say the three different factors. Like, what's the difference? Like, why do I always get it wrong? Keep thinking it's vibrations or like absorption.
Okay, listen, my dear. When I read this thing the first time, and that's why I said, hey, just remember that, okay, the backing material is also known as damping material. Here. Now, what damping failure mean is that's okay, cooling something down. Right, okay. You can say that's okay, if something goes like this, it's more vibration. Just think of, okay, as the crystals being as, okay, the crystals of a chandelier. You have a strong wind passing through that room. What's going to happen? Those crystals of your chandelier are going to just, okay, constantly moving as that breeze is flowing. That would be a continuous wave Doppler. Or you can say, no, not Doppler, sorry, continuous wave transducer, because it doesn't have a damping material. Did that make sense? Okay.
Yes.
Okay. Now you're going to say, as okay, what could be as okay a damping material for that? Well, okay, you can say, as okay, curtains in front, as okay, or you can, as okay, cover your windows with curtains. Now that may not take all of the wind, but at least that's okay. You can say it's okay, reduce, that's okay, the flow of the wind through that room. And okay, your chandelier's crystals, which was going like this, may just go, okay, it's okay like this, and there's a very strong breeze of wind coming. Did that make sense?
Yeah.
Right, okay. So that you can say is okay, backing material or damping material, pulse wave transducer, imaging transducer, now backing material, continuous wave transducer. Did that make sense?
Yes, thank you.
Okay. Then just comes, okay, those three consequences. Well, okay, just remember, okay, what are the consequences of your backing material? Low sensitivity, which we actually can say, yes, okay, is a disadvantage of the backing material. Because it will be, yes, okay, less sensitive to weak reflections. Did that make sense?
Yes.
But then you say, yes, okay, it has a broad bandwidth. And okay, it's a low quality factor, mainly because, okay, what we said when we did quality factor, we related that to your bandwidth. Okay, where we say bandwidth was mainly as, okay, quality factor or mainly as, okay, just your main frequency divided by the bandwidth. So when you have a greater bandwidth, yes, okay, you will have a lower quality factor. Whereas, okay, now when we go to, yes, okay, continuous wave transducer, which we did in this chapter here, practically, page 313. Now, the reason that is going to be, yes, okay, a continuous wave transducer, not Doppler, transducer, is that it doesn't have a backing material. Did that make sense? Now, since it doesn't have a backing material, it's okay, it's going to not have those three consequences of your backing material, but just the opposite. Which then will just be as, okay, we'll have a great sensitivity, a smaller or narrower bandwidth, and due to a narrow bandwidth, a high quality factor. Clear?
Yes.
Okay, we can then also check, oh yes, okay, chandelier in the living room with the wind. And say, okay, the frequencies, not the bandwidth, the frequency. Now you can say, okay, the greater the frequency of you can say, okay, it blows of the wind. Mainly because there was no damping material. Well, okay, every breeze or blow of the wind was going to just, okay, shake your crystals in the chandelier. So the frequency of your wind blowing and, okay, yes, the frequency at which, okay, yes, your crystal on the chandelier was blowing, yes, okay, vibrating was going to be the same. Did that make sense?
Yes.
Good. Whereas, okay, as for a pulse wave transducer, well, okay, it was going to be different. In that case, as okay, our frequency of that transducer was going to be as okay, dependent upon two factors: speed of sound in the PCT and the thickness of the PCT. We discussed that earlier, right?
Yes, we did.
Okay. So just look at it in this way. Okay. Now I have a big lamp hanging right here on top of my head. Okay. Okay. If I end up, God forbid, if I end up having, okay, it's like a big hole in the wall over here. And on a windy day, yes, okay, that lamp was going to just move. Right now, it is preventing us, okay, from doing so. Because, okay, there's a damping material between the outside world and my room, which is this wall here. Okay. But we don't want, okay, as our transducer to go on a complete standby. I have no frequency. They gotta have it. Okay. But mainly because, yes, okay, continuous wave transducers constantly move. Okay. That's why it's okay. They are used as what we could call as okay therapeutic transducers as well. Have any of you ever tried as okay those massage machines?
Yeah, I use physical therapy.
Right, okay. Okay. So yes, okay, you can actually that's okay set them at different speeds. But you can say okay, the more you just okay increase the speed at which they are firing, okay, what is that they're going to do? Warm up the tissues more. Did that make sense?
Yes.
Yeah, okay. So you can see that's okay, you can use that okay physiotherapy for that's okay for something at least here. Okay. So not even have those handheld things that okay, I mean it's okay, rub. But again, yes, okay, it strikes and it's okay. Okay, goes. So see, the only thing that's needed is, well, okay, you should just ask. Maybe my different, that's okay, explanation in the first place, that's okay, that make it okay. That's why I say, okay, let me go and see. Could there be another way by which we can explain it? And then it just clicks. Okay. And you can say, it's okay, your sample rate is greater than the velocity of blood. So yes, okay, you get the thing with no aliasing. Okay. So any other thoughts on any other topic?
I have a quick question.
Share.
What did you say the advantage and disadvantage was for the baseline shift?
No, there's no disadvantages for the baseline shift, my dear. I said that this, okay. Although that's okay, not mentioned in chapter 19, it'll become, they mentioned it in chapter 20 anyways. But the disadvantage of your, you can say it's okay, reducing or using a lower frequency transducer to get rid of aliasing is that that's not going to be suitable as okay in color Doppler. Yeah. Another thing that had a disadvantage was okay as increasing your scale. Now increasing your scale, that was the first step that we talked about, my dear, in terms of okay, getting rid of aliasing. And what that is going to do is it's going to it's okay make your system less sensitive to, or it's going to reduce its sensitivity to lower velocities. Did that make sense?
Yeah, thank
So
you.
if you increase your scale a lot, it will not be able to record as okay low velocities. So that's okay. That will mainly mean that okay, those velocities are going to just okay be so low that okay, as the system will not recognize them as a velocity at all, and it will show up as a zero Doppler shift. Now that's something that okay, yes, that we actually is okay will come across as one of the last topics in chapter number 20. So, but tomorrow goes, that's okay. Just a couple of topics that I was want you girls, that's okay. We're just going to use it as a cheat. First is going to be, it's okay, your linear sequential array transducer. Just make sure that you know how that fellow worked. Clear? And one topic, and we're going to use that as a cheat. Another thing is, well, okay, just make sure that, okay, yes, you know what reject is. Okay? And you'll find that in chapter number 12. No. Chapter 14, sorry. Chapter 14. Okay, ladies. So I guess that's all that I can offer for today for now. Now, those of you who intend to just okay attend the tutoring session, it will start at 2:30. Okay, and you should have been received. You should have received a link for that one. Okay, so see you girls, whoever wants to be there, in half an hour.
Thank you.
You're welcome, dear.